Okay. So this previous working definition that we had over here on the right about acids having H plus in the front of the formula, think HCl, HC2, H3O2, HF, like all of these, HNO3, all of these acids, oxyacids and binary acids that we named in honors chemistry, they always had an H plus cation in the front of the formula. And bases like sodium hydroxide, lithium hydroxide, and aluminum hydroxide, they always had this hydroxide anion at the back of the formula. That definition is called the, that's called the Arrhenius definition of acids and bases, okay? There we go. I'm gonna do acid work in red because I'm gonna try to start drilling into your heads here. The colors that you're going to see with our indicators, universal indicator turns red in the presence of H plus. Okay, so acids we're going to be working with in a red color. And when we talk bases, bases turn universal indicator blue. So I'll be working in blue whenever I refer to a base. Okay, but like I was saying, this definition is not good enough. It's just not comprehensive enough. We need a new definition. And this new definition is called the Bronsted-Lowry definition of acids and bases. And we'll start off with what a Bronsted-Lowry acid is. Okay, a Bronsted-Lowry acid is an H plus donor. Okay, so yes, it's got some H plus in its formula, not necessarily at the front of the formula anymore, but it has some H plus in it and it gives it away. Who does it give it away to? It gives it away to whatever the base is in the reaction. You know what? I don't like how my H looks. Yep. Okay. An acid is an H plus, there, that looks better, is an H plus donor. Okay. Another way to think about that is that acids produce H plus ions in solution. So whenever we're talking about acid behavior or base behavior, we are talking about things that are aqueous. All right, so again, what makes this an acid? The H plus. Okay. Bronsted-Lowry definition, H plus donor. Okay. Let's take a look at an example of this acid behavior that I'm talking about, this like giving away of an H plus. Let's work with an acid that we're familiar with, like HCl. We work with that acid all the time. When you put HCl in water, so HCl plus H2O. What's actually going on when you put HCl in water is the H from the HCl gets donated to the H2O. That's what I mean by an H plus donor, okay? So like the HCl gives away the H plus, draw that transfer to the H2O. When the water molecule gains an extra hydrogen, it becomes something called hydronium, which is H3O plus. This is called the hydronium ion. And of course, the chlorine is now just a chloride ion. That's like a lot to write out, okay? Oftentimes what we do, instead of drawing like it as a reaction with water, instead of like including the water and showing the water as hydronium with an extra H plus, what we really care about is just the extra H plus. So we can also, with acids, just leave the water out of the equation, right? We can just say, hey, HCl is an acid. And what that means is that when it's aqueous, it dissociates in water to produce H plus. Oh my God, my husband's sneeze is so loud. it produces H plus ions and chloride ions. These two reactions are saying the exact same thing. I know like this first one looks more complicated, but they're saying the same thing. What they're saying is that HCl is an acid. Why? Because it donates the H plus to water and either makes, in your head, hydronium, that's what makes it acidic, or you know what, when it goes into water, it dissociates, it produces a bunch of these extra H pluses, some of them are stuck onto water molecules as hydronium. That H plus is what makes this acidic. Now, I'd like you guys to notice that the arrow that I drew for both of these reactions, which like I said, are saying the exact same thing, I only drew one-way arrows, okay? I did not draw an equilibrium. The reason why I did not draw an equilibrium here is because HCl happens to be a strong acid, okay? What I mean by a strong acid is that it totally dissociates. Like you get maximum amounts of H3O plus and H plus, okay? So down below here, and I'm gonna scroll and I can't see you guys, so you just need to let me know if I'm going too fast here. We're gonna define what it means to be a strong acid. Okay. A strong acid dissociates completely in solution. In other words, it's producing maximum amounts of H plus. That's what makes it really acidic. And somebody asked last period, they were like, or this morning, is that going to make the pH really low? Yes, right? Like pH is a measurement of how much H plus is in solution. So we're going to talk about those measurements later in the week. So dissociates completely in solution, produces maximum amounts of H3O plus or H plus, same thing, okay, in solution. Oh, and you know what? I didn't label. Like here, I would label the HCl. This is an acid. Why is it an acid? Because it's giving away that H plus. Okay, label this here, the acid. This is the acid. Why is it the acid? Because it produces that H plus. Now, reactions that go almost all the way to the right and produce a ton of product, those are going to have very large K values, right? Like there's not even really an equilibrium here. You know what I mean? It's lying way to the right, tons of product. So if I were to measure an equilibrium constant for this reaction, I'd have a big K value. Okay, so you're going to have large K values. For acids, we call them A. We call it a Ka value. You know how we had like KEQ, KC, KP. Now we're going to have Ka for acids, Kb for bases, Kw for water. You're going to be sick of how many different subscripts we can put here for our equilibrium constant. Okay. So acids give away H pluses in solution or produce H plus or hydronium in solution. Strong ones do it a lot. Like they go all the way to the right, they produce lots and lots and lots of these products. And very little of this remains molecular, like together. So your next question hopefully is, how do I know if an acid is strong or not? Okay. And unfortunately, there's just a list that you kind of have to internalize. Okay. There are 7 strong acids. And they are HCl, HBr, HI. So hydrochloric, hydrobromic, hydroiodic. Those are our 3 binary strong acids. Then comes some oxyacids that are also strong. HNO3, nitric, H2SO4, sulfuric, HClO4, perchloric, and HClO3, chloric. Okay, so you just got to know them. Now, in your text, there's also a chart of relative strengths of acids and bases. Okay, so like their strength is going to be determined by their Ka value, right? So the bigger the Ka value, the stronger the acid. The smaller the Ka value, the weaker the acid. And there's a chart of that on page. You should be reading the sections. We're doing section 16.1 and 16.2. The relative strengths of these are on page 657. So that'd be something good to take a look at tonight. Any questions so far? If there are strong acids, guess what else there is? You guys are so smart. There's weak acids. Weak acid. For a weak acid, we're just going to have the opposite definition, right? So like instead of going all the way to the right, dissociating completely, producing maximum amounts of H+, a weak acid only does that a little bit. It doesn't donate all of its H+ ions, only a few of them. And you've got this equilibrium established here with a weak acid where you've got some of the ions, but you've actually got a lot of the molecule that remains as well. You've got a smaller Ka value. You've got a mix of reactants and products. So we say that like so. Weak acids dissociate partially in solution. Again, these are only in the presence of water. It's not that they can't be solids or liquids, it's more just that like we measure their behavior in water. So like you can actually, I do have containers of solid acid, like we call it an acid when it's sitting in the acid cabinet in the back hallway, but we don't get those free H pluses until we dissolve it in water. Okay, that was a side note. Weak acids, they dissociate partially in solution and they produce less H3O plus and H plus, and thus they are going to have smaller Ka values. And so because these Ka values are small, we need to indicate in the drawing of our reactions that there's this equilibrium being established here. So for strong acids, we draw a one-way arrow all the way to products. That's where the equilibrium lies, to the right. Weak acids, we're going to do our equilibrium arrows to indicate the fact that some of this acid is going to remain molecular. Okay. So how do I know it's a weak acid? Well, it's just not one of the 7 strong acids. Okay, so if it's not one of the 7 strong, it's weak. For example, HF. Okay, HF is a weak acid. I'm going to write this reaction 2 times. Once with water and once without, just like we did before. So HF in the presence of water. Hang on a second. My son, I think, is playing video games, which he's not allowed to do until 3 o'clock on his asynchronous days. Wait one. Okay. HF plus water, it's going to donate an H plus. Because it's an acid. Even if it's a weak acid, it's still an acid. It's going to donate its H plus to water. But I'm going to draw a double arrow this time, indicating that equilibrium, making the hydronium, and leaving the anion as F minus. Oh my gosh, I think this morning I wrote like chlorine there. It feels like I did at least. Maybe I didn't. Okay, so let's label everything. Okay, let's label the HF as an acid. Now, if acids are H plus donors, okay, then bases must be H plus acceptors. Like they're kind of the opposite of acids, okay? So the water in this case is acting as a base. Did I not define bases yet up here? Yeah, I didn't. We're gonna get to that, okay? But bases are the things that accept the H plus. And it's possible for a substance like water to act as an acid or act as a base, depending on what sort of situation it's in, what it's in solution with, okay? So this is the acid, this is acting as the base. What's different about this situation than the HCl is we have this equilibrium being established. And so that means that on the right-hand side, something's happening too, right? In order to go back the other way. So like for this reaction to go in reverse, the H plus has to go back to the F minus. Okay, there has to be a transfer of the H plus on this side in order for there to be an equilibrium. So on this side, the H3O plus is acting also as an acid. When it's on the right-hand side of the equation, we call the acid on the other side the conjugate acid, just to indicate that it's not like the primary player here. It's like the partner. This is the conjugate acid. And the F minus is what we call the conjugate base. This is the thing on the other side of the reaction that is accepting the H plus. The partnership of these two things, like this HF acid with the base that it forms, this guy here, so that with that little partnership right there between the HF and the F minus, that is called a conjugate acid base pair. And also the water with the H3O plus, that is also considered to be a conjugate acid base pair. And I'm not just giving you definitions to be annoying. Like being able to identify conjugate pairs matters. We'll talk about why it matters later, but it does matter. Like we're going to be able to tell a lot about this conjugate base if we know what its parent or conjugate acid is, okay? Now, that's like sort of like a big complicated looking thing because I included the water. But again, you don't have to include the water. Just like with the HCl, we can, instead of writing it as a reaction with water, actually like showing the H plus being donated, we could just simplify it. Blah, blah, blah. Simplify. Aqueous, forward, reverse, making H plus and F minus. Okay. And if I was labeling everything, the thing is like when you write it without the water, you can't exactly pair up all of the conjugates, you know, because you're missing the water and the H3O plus, you know, you're missing that. So this is like not the best way to write it if you're trying to identify conjugate pairs, but this is a perfectly acceptable way to write this reaction as well. Okay, so like this is the acid. Why is it an acid? Because it makes H plus in solution. Same thing here. Why is this an acid? Well, it makes H3O plus in solution. How does it do that? By donating its H plus. So for this example here of a weak acid, we are going to get less H3O plus or H plus because it's weak. Versus up above, when we were talking about HCl being an acid, here, this is what makes this acidic here, you're going to get more H3O plus or H plus because HCl is strong. One other thing to note here, you guys, that I kind of forgot to say is when we say H plus, you can also call H plus a proton because hydrogen has one proton. And it's not really just hydrogen because it lost its electron. So we can just say a proton donor, right? Because H plus is just literally a proton. So another way to define an acid is not just as an H plus donor, but a proton donor. So you'll hear me interchange H plus with proton. So just be mindful of that. All right, so now let's talk bases, okay? How did I do this? All right. A base is an H plus acceptor. Now, in the process of accepting this H plus, it ends up producing OH minus in solution. So that definition that we had before, that Arrhenius definition that we had for bases about, there being OH minus in solution, that's still good, right? Like the fact that something produces OH minus in solution is what makes it a base. But it turns out that that's not the only way. Like dissociating and producing OH minus is not the only way to get OH minus. Like you can actually also get OH minus in solution by this transfer of the H plus. And that'll make some more sense, or will make more sense when we write out a couple of these examples. Okay, so a base is an H plus acceptor producing OH minus in solution. It can do this, like I was saying, in two different ways. Okay, it can do it by just having OH minus and dissociating. Okay, that's one way to get this OH minus. It just breaks apart and produces OH minus. The other way to get OH minus is from the H plus accepting. And we'll do two different examples showing each of those. All right. So my first example, hang on, I just want to make sure that these notes match my acid note format. Oh yeah, I should say in solution, and it's a proton acceptor. Yeah, I did say in solution, meaning aqueous. H plus acceptor, or you could say proton acceptor. Okay. Let's take a look at an example of a strong base. So a strong base would look like this. It would have hydroxide in it. We'll write a rule for strong bases. Okay, so if I have a metal hydroxide, like it's a metal cation with this hydroxide anion, and I put it in water, it dissociates completely into strontium ions. And for every one strontium ion, I produce 2 hydroxide ions. So there you go. Like there's the OH minus. There's nothing tricky about it, right? Like this is a base. Why is it a base? Because it produces OH minus in solution. So this right here is an example of how a base makes OH minus just by dissociating. This example that I just gave you was that one of those one-way arrow situations, meaning that strontium hydroxide dissociates completely. It's a strong base. Okay, so just like we had a definition for a strong acid, we also have a definition for a strong base. And it's the same definition as strong acid. It's just not talking about H plus, it's talking about OH minus. Okay, so a strong base dissociates completely. And produces maximum amounts of OH minus. They are going to have large KB. values because they're making lots of products. You know if something's a strong base, like the rule for strong bases is this. Group 1 and group 2 metal hydroxides are strong. Now by group 1 and group 2, I mean the groups on the periodic table, right? Up and down columns. Group 1, your alkali metals. Group 2, your alkaline earth metals, okay? Any of those metals bonded to hydroxide are strong bases. Now they're not all equal strength. Again, there are relative strengths here. In fact, like the lighter group 2 metals, like beryllium and magnesium and calcium, those aren't super strong. It's more like the heavier group 2 metal hydroxides. Again, these are relative numbers based on their KB values. Okay, so like you could look up their values in the back of the book. None of these strong bases are listed on page 657, like I was talking about, but you get the idea. Group 1 and group 2 metal hydroxides are strong. They produce lots of OH minus. If I had a metal hydroxide that was not group 1 or group 2, like aluminum hydroxide or iron hydroxide or zinc hydroxide, like any of the transition metals or aluminum, those are going to be weak. So you would write this same dissociation, but with the two-way arrow. Okay. So let's define that. I don't know why I paused there. Okay, so a weak base dissociates partially. Produces less OH minus in solution. And they are going to have small KB values. So like we did with the acid, strong base, one-way arrow. Weak base, two-way arrow. This example up here of strontium hydroxide, it's going to give me lots of OH minus as SrOH2 is strong. I'm really into double underlining today, apparently. Okay. So let's take a look at a weak base. And let's do another hydroxide, right? Like let's look at another example of just dissociation. I still haven't touched this whole H+ accepting thing yet. I'll get to that. But let's look at a dissociation of a weak metal hydroxide and just compare how it looks to that strontium hydroxide example. It's really simple. Aluminum hydroxide in solution. Just draw a two-way arrow. Dissociates into aluminum ions and 3 OH minus. Remember, these coefficients, you guys, are just coming from the formula of the compound. Okay, so here we're gonna get, like, even though it's like a 1 to 3 proportion, we're gonna get less OH minus because aluminum hydroxide is weak. So you'll get a little bit, but the KB would indicate the reaction lies more to the left, that in fact you're going to have more of it molecular, stuck together, and not free floating as OH minus ions in solution, which is what makes the thing basic. Okay. What we need to look at now, and this is sort of the whole reason, honestly, it's the weak bases that were the reason why we really needed a new definition for acids and bases. You know, the acids, you don't even need to like show the H plus being donated, like just separating it into H plus is good enough, you know? So like, didn't really need it, the new definition for acids, but there are bases, like there are substances that can produce OH minus without having any OH minus in the formula. It's like, well, how does that happen? By accepting an H plus. So we have to look at that example, right? So what I'm referring to here is now taking a look at how does H plus exception produce OH minus in solution. So this is how. And this is your most common weak base that every test and textbook likes to use. Ammonia, okay? Ammonia is a weak base. Now, for the weak base reactions, you have to include water. There's no shortcut. There's no just like writing the dissociation with the two different arrows. Because like I look at NH3, there's no hydroxide there. Okay, so you can take that shortcut and leave the water out of it for acids, strong or weak. And you definitely don't need the water for the strong bases or the hydroxide bases, any of the hydroxide bases. But for these other weak bases that are not metal hydroxides, you have to include water in the formula, or the reaction, I mean. So here we go. If NH3 is a base, by the Bronsted-Lowry definition, it's going to accept an H+. Well, where is it going to get that H+ from? It's going to get the H+ from the water. So in this case, the water is actually acting like an acid. And the NH3 is behaving as a base. Like I said before, you know, like when we were doing the acid example with HCl, the H2O was accepting the H+, which made the water a base. Water can do both. There are a bunch of substances that can do both. Okay, so when this happens, and I'm going to draw a two-way arrow because that's a weak base, when NH3 gains an H+, it's going to become ammonium, NH4+. And it's going to leave the water as OH minus. And if that's confusing to you, like just think about a water molecule, right? You've got a water molecule here, looks like this. If one of these hydrogens runs away, bye-bye, what are you left with? You're left with OH with an extra electron, right? From this shared bond, because it ran away as H+, it didn't take its shared electron with it. So what's left? This thing with a 1 minus, okay? So that's where that hydroxide comes from. And that's what makes this solution basic, right? So here we are able to produce OH minus in solution without any OH minus in our formula, okay? And of course we have the same thing going on over here because there's equilibrium, which means the ammonium is not very stable. Like it doesn't like that extra H+. And I've got this negative charge over here. So it's like, here, fine, hydroxide, take the H+ back. And when the hydroxide takes the H+ back, boom, we're at water and NH3 again. So over on this other side, the NH4+ is behaving as an acid, but we're going to call it the conjugate acid. I'll just abbreviate. And the hydroxide is the conjugate base. And just like we had before, we have these conjugate pairs, okay? So NH3 is the base, its conjugate acid is NH4+. That is your conjugate acid base pair. And the water with the hydroxide. That is your other conjugate acid base pair. And just like the aluminum hydroxide, because NH3 is a weak base, you're not going to get a lot of OH minus, okay? You're going to get kind of a little bit OH minus because NH3 is weak. So you're going to see a lot of formulas with hydrogens in them that are not acids, right? Like NH3 is not an acid, okay? And you're like, but it's got hydrogen. Yeah, I know, okay? But those hydrogens are not in the front of the formula. Those are not ionizable hydrogens. Those are not hydrogens that want to come off. And you're wondering, like, why don't they want to come off? Well, like, let's think about the structure of NH3. This thing with its lone pair right here, right? These electrons attract hydrogens, okay? If there's any hydrogen, if there's any polar hydrogen in water, it's like this partially positive hydrogen is really attracted to this lone pair here on the ammonia. And that's what grabs that hydrogen off of the water to turn it into NH4 with a 1+ charge. Okay, so just because something has a hydrogen in it does not make it an acid. Okay, so you're typically going to recognize acids because of the hydrogen at the front of the formula. Or, am I ready to scroll? Hopefully I'm ready to scroll. I'll scroll back down if we need to. So like, yes, most of these acids, most of the way I've written these acids all have hydrogen at the front of the formula. But there are organic acids. Like, don't forget about the organic acids that we learned about sort of earlier in the year, where you've got like a carbon chain, you know, so like carbon, 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 however many carbons there are. And at the end of that carbon chain, you have a carbon, double bond oxygen, OH group, this COOH group. This COOH group at the end of an organic acid, this confuses people. They think, oh, look, OH, that's a hydroxide ion. No, it's not, okay? And this carbon chain can continue for as many carbons as we want. This right here is an ionizable hydrogen. Like, this is a very partially positive hydrogen that can come popping off in solution. And that's what makes this acidic, right? The fact that this hydrogen can pop off. Okay, so that is not a hydroxide ion in an organic acid. That is an ionizable proton. Okay, so acids typically, yes, have H's in the front of the formula, but the organic acids will have this COOH group. Very important, okay? And now you're going to recognize something like NH3 as a base, right? And not as an acid just because it has a hydrogen. Okay, so you got to think about it a little bit more deeply than that. Okay, I think that's all I need to